Okay, is it recording? Okay. So this section is about independent spaces and dimension. The basis of a vector space is a linearly independent subset of the vector space that spans it. There are an infinite amount of bases for any given vector subspace. Any vector space has a basis, and if a vector space is a finite basis, then all bases of V are finite and have the same number of elements. The number of elements in a basis is called the dimension, written as DIM, and that's the number of elements in any one of its bases. The dimension of Rn is n for any natural number n. If S is a subset of a vector space A, if S is a subset of a vector space V, then S is a linearly independent spanning set for V, if and only if S is a minimal spanning subset of V, if and only if S is a maximal linearly independent subset of V. What that means is that if you have a set S that spans a vector space V, and if you add any vector to S, it will no longer, or no, if you have a set S and you take away any vector from S, it will no longer span V. Similarly, if you have a set S and if you add any other vector to S, it will no longer be linearly independent. And S is both spanning and linearly independent. Yeah, that's what I was just saying. So for a vector space V, any spanning set can be reduced to a minimal spanning set, aka a basis, and any linearly independent set can be added. Well, you can add any vector to well, not any vector. You can add a certain vector to any linearly independent subset to form a basis. It might have to be one vector, might have to be two, depends. Any spanning subset of V contains a basis of V. If a matrix A with size m by n does not have a full row rank, then this happens. I think my mouse is dying. Okay. If a matrix of size m by n does not have a full row rank, then the equation ax equals b does not have a solution for every b, which is equivalent to, which means that that Rm is not equal to the column space of A, which means that the columns of A do not span Rm. If A has full column rank, then all columns of A are linearly independent. I'm not sure if this was given to us in a previous section or not. That's a lot of examples. Any set of n vectors in Rm are linearly independent if n is greater than m. Or linearly dependent, sorry. So for example, if you have r cubed and you have 4 vectors, then it's linearly dependent. If a set B with n vectors is a basis of V, then every V in the set in every V in the space V is a unique linear combination of the vectors in V. Yeah, that's just a lot of examples. Any questions?
Do you think we can like post Neha's notes and Padel's notes in one specific channel since they have a lot of examples?
Yeah, probably. Unless the files are too big.
You have this. You have Discord Premium. I mean,
Oh yeah, I do have Nitro. Yeah, someone gifted
you have
me.
Nitro.
I think it's classic. I'm not sure if it qualifies.
Oh, no, I'm not sure.
Yeah, I'm not sure. I'll try.
Okay.
Any other questions? There's a part 2 as well. Okay, let's move on. So if you have an n by n matrix that is invertible, then the columns of that matrix will form a basis of Rn. Okay, now the basis of the column space. Okay. If you have a matrix A, it doesn't matter if the columns are linearly independent or dependent or whatever. And if you find that it has a certain amount of pivot columns, then those pivot columns are linearly independent, and so they span the column space. So the base, so since they're linearly independent, and since they span the column space, they form a basis of the column space. Something I think I forgot to mention, but to prove that something is a basis, you need to say that it's a linearly independent set, and also that it spans the space. Both of those are important. You can't leave one out. And the row space, the subspace of Rn spanned by the rows of A. So just like the column space was the set of linear combinations of each column, the row space is the set of all linear combinations of all the rows of n of A, which can also be written as the span of the columns of the transpose of A. So it's a column space of A transpose. The benefit of the row space is that when you apply elementary row operations to a matrix, the span doesn't change because you're keeping the rows intact. Whereas if you're taking the REF, you're changing the columns. So, well, since you're rearranging rows, the columns will change. So the column space of the REF is not the same as the column space of the original matrix. The row space, the row space is the span of the rows of A, which is the span of the rows of the reduced row echelon form of A, which is the span of the pivot rows of either A or the reduced row echelon form of A. And the pivot rows are linearly independent. So the basis of the row space, the pivot rows of A will form a basis for the row space, since they're linearly independent and they span the row space. Now for null space, doesn't doesn't say it. Okay, if you have a matrix that has um, exactly one solution for ax plus b, ax equals b for all b, then you'll have that the only solution to ax equals 0 will be the 0 vector, and so the in that case the null space would be the 0 vector, or sorry, the null space would be the 0 vector. This set containing only the 0 vector, and so the basis of the null space will be the empty set. And to find the span of the null space, all you have to do is find the special solutions of ax equals 0. Yeah, and that's because they're linearly independent and they span the null space. So the special solutions are null space. The set of special solutions will be a basis for the null space. And that's it. Any questions? From the notes, it sounds really easy, but I feel like the problems will be really hard.
Yeah, I kind of agree with that. The notes sounds pretty easy.
Okay, let's look at some of the textbook problems. This one has a different list of problems. Okay, this is more comprehensive. It includes the other one as well. Okay, let's do 2. Let's do problem 2 from section 3.4 in the textbook. Let's take like 5 minutes to do it on our own.
It's been about 5 minutes.
Yeah, I think so. Okay, I can share. I'm not completely done though. Looks like it's working. Okay. Yeah, what I did was I set I put these vectors together in a matrix, and I started taking the REF of this matrix. It looks like the rank of this matrix is 3. So the number of linearly independent sets, the number of linearly independent vectors is 3. It looks like you can take the first 3 vectors and they'll be linearly independent. Because I can, well, I have 3 pivots in the first 3 columns. So I think the answer is 3.
So the last 3 vectors are going to be the independent vectors they are asking about.
I got the first 3 vectors.
Yeah, in the first 3 vectors you found the pivot. So
Yeah.
uh
Okay, so you know the last row has zeros, right?
yeah.
So the rank of this matrix must be 3, right? It can't be 4.
Mm-hmm. Yeah.
So there's exactly 3 pivots. So the rank is 3.
Mm-hmm.
So that means that the size of the largest the size of any basis of these 4 vectors is 3.
Yeah. Yeah.
So any 3 vectors, any 3 linearly independent vectors, will fulfill the that property. But they're not asking for a set of vectors. They're just asking how many of them there are.
Okay. Okay.
So in theory, I guess I could have rearranged the columns, and maybe I would have found a different permutation of columns. Maybe I would have found this column and this column and this column were independent. But it doesn't matter as long as I got 3.
It's the same process I did. I made an arithmetic error, but I did the same
Yeah.
thing. And it shouldn't matter how you arrange the columns, because if you reduce it to REF or REF, you're gonna get the same rank, and that's always gonna be the highest number.
Right. And actually, I guess this is REF. This isn't RREF, but it's REF, which I think that works.
Yeah.
Any questions? Okay, 13. Oh, actually, wait, I might be skipping problems. Yeah, let's see. Yeah, let's do 13. Let's just do the first matrix, because or yeah, let's do all of 13. Let's take like 15 minutes to do all of 13. It's a very long problem, but I think it's very important.
Do 10 minutes. You can
15.
just
What section are we on, just to be clear?
This is 3.4.
Okay.
I know I said 15 minutes, but does anyone really need more time?
I was gonna say it's not.
Yeah, I hadn't read the problem correctly. I thought it was find.
It was more like 5.
Yeah, I thought it said find all of those spaces.
Does anyone need more time?
Okay. Yeah, I'll share it then. Yeah. So I started with the matrix A. I started to compute the reduced row echelon form of A. I reduced it to this point where I realized that it's equal to matrix U, and I noticed that I found U by going through the process of finding the REF of A, which means the row space was preserved, which means, and since these two A and U have the same reduced row echelon form, they're gonna have the same row space as well. So two spaces that are the same are the row space of A and the row space of U.
The dimensions aren't too hard to find either. You just find the rank and
Yeah.
they're both the same dimensions and same rank, so they're gonna have the same dimensions for all of their subspaces.
Any questions?
Next problem.
Okay.
Somebody has.
That was 13? Okay, 16. Nah. Okay, let's do 26. I think 26 is something we can expect to see. Something similar to 26. Because there was a homework problem like this as well. Let's take like 10 minutes to do 26. Wait, I just realized that's gonna be a very long problem. Let's just do A for now. Or no, let's do C. I think C looks the most complicated. Let's just do C for now. Should we go over it?
Yeah,
Or do we need
let's
more time?
walk through it.
Okay.
All right, so does everyone remember what a skew symmetric matrix is?
No.
Okay.
But doesn't tell you?
Yeah, it gives you the general idea, but you might not remember the exact structure. So a skew symmetric matrix it's not, I don't think it's actually symmetrical, but if you flip it, it's equal to its negative. Which basically means that it's zeros along the diagonals, and basically when you flip over to the other side, it's negative. So it's basically mirrored in negative across the other side. When you draw out the matrix, you can sort of probably the way. Did you get the answer, Vishnu?
Kind of. Almost.
Okay.
I missed one detail.
I don't have my work on digital, but you're probably going to outline what a generic 3x3 skew symmetric matrix is going to look like. You'll have zeros in the diagonals. If we go in order, it should be something like 0, A, B, negative B, or sorry, I use different variables, but you're basically going to set it up with variables, and then you're going to break it up into a linear combination form. So you'll maybe say A times the matrix where you have, you know, row 1, column 2 flipped over to row 2, column 1 negative. And you'll basically set that up for each of the variables you have in the matrix. And what you'll find is that it should be, you should only need 3x3 matrices to create the linear combinations. And that is all going to be your dimension. It's easier if you've done problem B. 26 is meant to be done in order, but you can still figure out C if you know what skew symmetric matrix is. Does that make sense?
Wait, so sorry, I kind of tuned out. What'd you get for the answer? Dimension?
3.
3. Yeah. Yeah. I can share my screen. I mean, I'll go over for like a minute or two. Yeah, so this is basically the definition of skew symmetric matrix. It's where you have a generic matrix. It says 3x3 matrix. Every entry in the matrix is equal to the negative of the element that's across from it over the diagonal. So A equals negative A, B equals negative D, E equals negative E, G equals negative C, H equals negative F, and I equals negative I. For A, E, and I, you're setting it equal to its own negative, which means it's equal to 0. So you have 0, 0. So the main diagonal is zeros. And then you have B equals negative D, G equals negative C, H equals negative F. So you basically have three you basically have 3 independent variables, which means you have 3 independent if you were to write this as a linear system of equations, you'd have 3 independent you'd have 3 pivot variables and 3 free variables. Well, 3 pivot variables and 6 free variables if you count the diagonal variables as free variables. So you have 3 pivot variables, which means the rank is 3, which means the basis of which means any basis of the set of the space has dimension 3, or any basis has size 3, which means the dimension of the space is 3.
You'd
Is that
also,
accurate?
yeah, you'd also need to draw out the component 3x3 matrices, but it's pretty simple once you've outlined it. I did skip a step. I didn't label every single vertice. I just started with a kind of a range, but this is probably a more thorough way of doing it. You just need to make sure that in your final answer, you do actually find the basis with the various matrices.
Yeah.
Yeah, this is the same logic.
Yeah, I didn't find the basis.
I had a question, if, before we move on to another example.
Yeah.
In the exam review that was posted a little while back, exam2review.pdf, there's a part where it talks about symmetric matrices that I don't quite understand. Does anyone
Where is
help?
it?
It would be on page 2.
No, where's the PDF?
I believe it was posted in notes resources. Yes. So exam2review, I believe it was pinned.
Oh, okay.
Or
Yeah.
so on that page it says A transverse A is symmetric Y, and then A transverse is symmetric Y, and I'm not quite sure what their proofs are. Like I know how to prove it vigorously because I think we've done it before, where you can show that everything just gets multiplied together. But like, what is the proof that they're showing in here?
Oh, okay. It's that if you have, okay, let's call A transpose B, and let's call A C.
Yeah.
So we have BC transpose equals C transpose times B transpose. And C transpose is A transpose since A equals C. And B transpose is A transpose transpose, which is A.
Quite follow that verbally, but it seems like it's starting from a symmetric matrix. And maybe
Oh no, it's not calling it symmetric. It's saying let S1 equal A transpose A. It's not claiming S1 is symmetric until okay, yeah, I see what you mean. It's worded pretty badly.
no, I get what it's saying. So it takes S1, assuming it's symmetric, and then it flips it and shows that
It's equal to itself.
yes. Okay, I get what it's doing now. Okay, we're good.
Yeah. Okay, that was 26, right?
It's
I would say 35, but I think that's pretty easy. Or wait. Yeah, let's do 35. It's not that easy. At least the second part isn't too easy. Let's do 35. Yeah, should we go over it?
Sure. I think I figured out the first one, but I wasn't quite sure of how to do the second one properly.
Yeah, I wasn't either.
I figured out the second part, but not the first one.
Oh.
Okay, perfect. I'll share my screen for the first part. Yeah, for the first part, the set P3, the subspace, the vector space of all polynomials whose degree is 3 or less, can be written as all polynomials in the form ax cubed plus bx squared plus cx plus d, where a, b, c, and d are real numbers. Which means, and so ax cubed, sorry, x cubed, x squared, x, and 1 are a basis for P3 because they are linearly independent, and also because they span P3. They're all basically P3 is the set of all linear combinations of these four, which means P3. P3 is spanned by these 4 vectors. These 4 vectors are linearly independent because I mean, it's pretty obvious.
Yeah, that was the thing, is that it seemed obvious, but I wasn't quite sure of the exact.
Yeah, I'm not.
proper
I
way.
don't know a formal way to prove that they're.
Do we have answer sheets for these or anything like that?
Yeah, there's one on the official website.
Okay, I got the same basis that you did.
Okay.
So good thing on that. The second part, once again, depending on how you do it, I either got that it's either it's either 4, 1, or 0. I'm not sure.
Dimension?
Yeah. I well actually it
It
wouldn't
can't
be
be. It
1.
can't be 0.
Actually, I think it could. Because it's stating that if it equals 0, what you're getting is that in place of x, you have 1. In place of x squared, you have 1.
1.
In cubed, it's 1. So when you multiply those out, what you basically get is a plus b plus c plus d equals
Oh, equals
0.
0. Okay. Okay.
But it depends on whether or not you're allowed to simplify. Because if it all equals 0, then the value of each combination is always going to be 0. So I don't know. Would it be dimension 0 or not? I don't know. I might be going too far though.
I don't know if I did it right, but I did it like if it was a null space. I did like basically what would A be, like if A was the pivot and you assigned like B equals 1. Like I got 3 vectors.
I don't understand.
Like I did it like if it was a null space, so basically A is the since you have A plus B plus C plus D equals 0, then like A is the pivot, and then B equals 1, C equals 0, and D equals 0.
Oh, okay. Okay. 1 0 0 0 1 0 0 0 1. Right?
Yeah, but like if B equals 1, then A would be -1. So like the 3 vectors I got were like -1, 1, 0, 0, -1, 0, 1, 0, and then -1, 0, 0, 1.
Oh wait. Someone shared in study room.
Anyone
Someone
find
shared.
the solution?
Yeah, from the textbook's website. Wait.
I
So
see
what?
the answers, but like, how did anyone like solve out that answer? Because that
Wait. I
seems
think that's
cool.
that's right. What'd you get?
Like I did it like kind of like a null space, and
Yeah.
I
What was the answer?
so 3 vectors. -1, 1, 0, 0, -1, 0, 1, 0, and then -1, 0, 0, 1 for A, B, C, D.
I think that works. That they got x minus 1, x squared minus 1, x cubed minus 1. Which would be. Yeah, I think that works. You're basically doing the same thing. They're setting the last column as a pivot variable instead of
Yeah.
the first column as a pivot variable.
How do you set this up as a matrix? Because I wanted to do that, but I wasn't sure how to do it.
Okay, let's try it.
I think we'd like to work this out at some point. Either, well, it depends on
Have
where
a
we
blank matrix. And then, okay, our vector will be a 4x1 matrix. And the vector will be 1 x squared x cubed, right? Do we want to do 1 x squared x cubed, or do we want to do x cubed x squared x at 1? Let's go the other way.
I don't know what I'm saying.
Yeah, and our matrix would be we're trying to solve a system of equations, aren't we? P of 1 equals 0, then okay, yeah, this is a homogeneous system. Ax cubed plus bx squared plus dx plus d equals 0. Yeah, what would our matrix be then?
Would the matrix just be like a row vector A, B, C, D? Or would A, B, C, D be,
Just one row?
yeah.
Anyone else have any ideas, or is everyone else in the chat?
Yeah, I mean, I think we'd have to do a single row vector. Right? I mean, does this not work?
Yeah, I think that's right.
Are you allowed to take yeah, I mean, when you set this equal to 0, then you'll get exactly one pivot. Well, yeah, one pivot column and three free columns, right? Yeah, I think you did it perfectly. Oh, okay. I think what they did, as opposed to what you did, they probably went the other way. So they went 1 x squared x cubed, and so they got 1 was their free column, or no, 1 was a pivot variable, or the column corresponding to 1 would be their pivot column. The other columns would be free, and so they got see, x minus 1, or no, they got x plus 1 equals 0, or no.
Oh, so they just like flipped it, basically.
Yeah, I think so.
Y'all still figuring that out? Can we
No,
see?
I mean, I get it, but I get how
Can
they
you
did
show
it.
it? Because I don't see it.
How they got their answer?
Yeah, if y'all understand it, if y'all show it.
Yeah, I mean, I'm still processing it, but basically what they did was they set up their vector in the opposite way that we did. So this was their vector. This was their coefficient matrix. This is their solution matrix, the zero vector essentially. And when you multiply this, you get, well, first of all, you know p of x equals 1, right? Or sorry, x equals 1. So this x would be a 1, this x would be a 1, this x would be a 1. So a plus b plus c plus d equals 0. You set a as free as a pivot variable. B, c, and d are free. A see. So I should probably write this out. Write this out.
Just
Okay, you
You've
basically have
got-
this matrix.
yes.
right? You have this system, this augmented matrix, and then this is your pivot variable, pivot column, and so then you set these as your free columns. So you do 1 0 0 0 1 0 0 0 1, right? And so you do a plus b equals 0. A must be equal to negative b. And you assume a is 1. A plus c equals 0. A equals negative c. So c equals negative 1. A plus d equals 0, which means a equals negative d. Since a equals 0, d equals negative 1. And so you have 1, negative 1, negative, or no. You have,
It would be good if you could write some of this. I have bad number
Yeah.
memory, so
Okay.
that's a lot of numbers to keep.
yeah,
That
I do that a
one.
lot. Okay. You can have the system of equations. But actually, now I'm drawing a blank. How exactly do you find the special solutions again?
Special solutions are, you basically use one of the free columns, then negate it using the pivot columns. So you're basically gonna, the easiest way is do one in the free column you're doing, and then make the pivot columns equal to negative whatever that column is. So you would put 1 in B and then make A, negative B.
Okay.
And everything else would be 0. But that gives
No,
you
there's-
null space.
There's a specific way you do it, right? Do you do it as a system of equations, or do you still do it in matrix form?
Like I just assigned b equals 1 and then c and d equals 0, and I solved for a, which is like obviously negative 1 since that has to equal 0.
Right. Okay. Actually, wait. Before we do that, we let a equals 1. Right. So this becomes a 1. This gives you a 1 for the first entry. So in other words, it's a pivot, right? Now, you find the special solutions of this matrix, and so you set b equals to 1, right? So, or no, you don't set b equals 1. You set the okay, no. Do you let a equal 1 or not?
I don't think you set value.
Yeah,
don't
I
think-
just solved for a since it was the pivot.
Yeah.
So
Yeah.
I assigned like 1 and 0 to the free one.
So okay, if you let b equal 1, c equals 0, and d equals 0, then you get 1
I get it
0
like that.
0 equals 0, right? And so then you just subtract a minus 1, or a plus 1 equals 0, a equals negative 1. Then if you set b equals 0, c equals 1, d equals 0, you get a 0 1 0. So a equals negative 1. And so your special solutions, if you plug them back in here, you get negative 1 1 0 0, negative 1 0 1 0, negative 1 0 0 1, which means when you multiply this and these special solution row vectors and this matrix, you'll get 1 minus x, 1 minus x squared, and 1 minus x cubed. And you can multiply all of them by negative 1 and still without changing the basis, and you'll get x cubed minus 1, x squared minus 1, and x minus 1.
Yep.
Which is how they got their answer.
So I get what you're talking about, the null space. So you're basically letting the x squared, and the x cubed do whatever they want, but the kind of x to the 0 is just going to negate whatever they do to make sure the total is 0. Okay. Because whatever, so let's say the coefficient for, x is going to be 4.
Right.
You just need to have -4 for whatever just the displacement on the equation is, the x to the 0 power is. And you do that for every other one because you're making
Yeah.
the ones place your pivot column. You just have that account for whatever you do in the other columns, and that balances it out. So
Yeah.
what you did in that last shot is correct because you can just derive these bases from those.
Yeah. And also we know x equals 1, so that's why we won't ever get a 4 or something.
Okay. Sheesh.
Yeah, that was a long one.
Um,
I'm not sure if they're gonna put something this hard on the exam.
I feel like they might get theoretical with it, but yeah, I don't know.
I
if
think
we'll see
26
something
is more likely for this concept.
in the review. It does say there's likely going to be a polynomial one on there, so understanding how to work with polynomials is probably a good idea, but I don't
Okay.
think it'll be this specific.
Yeah.
Okay. Sounds good.
That's all that's in the recommended problems.
Awesome.
Any other questions on this section? Okay. What time for tomorrow? 8 p.m.
Yeah.
Maybe probably be able to make it.
Okay. Let's do 8 p.m. tomorrow. That should be the last one. 3.5 tomorrow.
That's good.
Yep.
Okay. Is the recording still going?
Probably. Well.
Yep.
Yeah.